All right. Had to reset my router this morning. Sorry about that. That's why I'm a few minutes late. And yeah, so just a reminder of due dates and such. 3.6, both parts is due, are due. It's kind of weird, the singular and pluralness right there, but that is due today. You also have your test 1 on chapter 1, which is 1.2 through 1.7, as well as 3.6. So no 1.1, and 3.6 feels more like 1.8. So that's today and tomorrow. It's online in my math lab. Remember that you have to submit your work within 15 minutes of the test. Remember, no work means I could remove your grade entirely. So everyone must show work. Everyone must show work. This is pre-calculus. You have to show work in pre-calculus. The review assignment is still up in the homework section. I'm kind of surprised at how few people have even opened this assignment. I think it would be a very good idea for you to focus on the review before the test, but what would I know? And I don't think I gave a homework due date last time for 2.1. If I'm wrong, someone can say something in the chat, but I don't remember saying this. So I'm just going to say it's a week from today, and then 2.2 will be finished. So that will also be due a week from today. Since we're a few minutes behind, I don't want to waste any more time yapping. You've already heard about how the test is going to run, so let's go ahead and get into it. All right.
Oh, wait, that's too far back. 2.2. There we go. All right, welcome back, everyone. I hope we all had a good weekend. Remember that test 1 is up. Let me rephrase that. The time to take test 1 is up. So please understand that how everything went, that's how it's going to work unless I decide to change things. Notice the similar to the test, and that will continue. It wasn't a terrible experience for everyone. The grades kind of came in as I expected in terms of distribution, but we're not going to talk about that. We're just going to move on back into 2.2 where we left off. So just very quickly refreshing on what we covered last time in 2.2. We talked about how functions are increasing, decreasing, or constant, and we talk about these in terms of their x values, in terms of going from left to right. So increasing means going right and up, decreasing going right and down, constant, it's just going right and not up or down. We said that you're going to describe this with interval notation, and that it is absolutely important to only use parentheses to describe where things are increasing, decreasing, or constant. If you use a bracket, it's automatically wrong, and it's not even a partial credit situation. And we also reminded us to always use the x values. This is a classic issue when it comes test time, is that people will put a y value in there instead of an x value, and again, automatically wrong. We did some examples. We talked about relative extrema, how we have maxima and minima, and we're not necessarily talking singular. We can have several relative maxima and several relative minima. And that these are just the tops of hills and the bottoms of valleys. We think about it if you were to zoom in on just a tiny little region around it, and then in that tiny little region around it, both sides either point up or both sides point down. Like these little zoomed in windows of the blue and red respectively. We did some examples. We talked about how they're located at the x value and they are the y value, that the English, the language that is very important. And then we started talking about piecewise defined functions, which we had seen some examples of, believe it or not, just like graphically speaking. And we did like domains and ranges of them and whether they were functions. But now we're going to learn how to actually construct them. So graph the piecewise defined function is going to be this first example we get into today. And we said that these things are divided up. Why didn't it change color? This thing is so weird sometimes. What? Technology. So you're just imagining these things separated. So like this is one function and this is another function, but the things on the right tell you where they're valid. So this function is x plus 3 sometimes, and it's 1 sometimes. When is it x plus 3? Whenever you're using x values less than or equal to 2. When is it just 1? Whenever you're using x values greater than 2. So if I want to plug in x equals 7, I'm supposed to plug it into the bottom. If I want to plug in x equals 0, I have to plug it into the top. If I want to plug in x equals negative 4,000, top. positive 4,000 bottom based on this inequality over here. Now, if I wanted to find out what happens at f of 2, technically you're only supposed to plug it in here, but for graphing, we said that you will also plug it into the bordered one, even though it's not technically valid, and we'll use an open circle for that. So that's important so we can see where these things go up to. Okay, so let's see. The top one is for x is less than or equal to 2. Now this is x plus 3. Now this is something you should already know, but this is a line with a certain slope and a certain intercept. We will be discussing that in the next section in case you need a refresher, but we're going to go quicker than it would have been in Algebra 1 or Algebra 2. So for x plus 3, let's just say you have no idea what this looks like. Let's do 3 different x values. Let's do 0, 1, and 2. So for the top one, the top function, the x plus 3, we're going to do a table of values with x equals 0, 1, and 2. I don't have to use 0, 1, and 2. I could use -5, -2, and +1, and that would get me the accurate graph. But I do want to go up to 2. Again, the borders are very important to include in both of them. So for the y values, we're just plugging these in to x plus 3. So when x equals 0, that says that y is going to equal to 0 plus 3, which is 3. So we get 0, 3. When x equals 1, that says that y is going to equal 1 plus 3, which is 4. Again, you're just plugging it in here. That's all we're doing with the x values. So it's 4. And when x equals 2, you get y equals 2 plus 3, which is 5. So there are a table of values for the top function, the x plus 3, going up to its border. Now I could plug in -1 and -2 and -1,000,000, and we would just kind of see the same pattern continue. For the bottom function, the f of x equals 1, this is only valid when x is bigger than 2. So we could do, since I did 3 values, maybe we do 3, 4, and 5, or 5, 7, and 20. But I'm going to do 2, 3, and 4. The 2 is that thing I mentioned earlier that's highlighted. It is a good idea to plug in the boundaries even if it isn't included. X is bigger than 2 does not have the or equals. See, it doesn't have it. So technically 2 is not part of the function, but this is where it will go up to and stop. So that's why I put a little asterisk next to this. Now, when x equals 2, this is where we're plugging into, but there is no x to plug in. This is what's known as a constant function, something we actually just referenced earlier in the section. Because no matter what you plug in for an x value, the f of x, the output, the y value is always 1. That's what this says. This says that no matter what the x value is, y equals 1. When you try and plug in x equals 3, you can't, so y equals 1. When you try and plug in x equals 4, you can't, so y is 1. The output is always 1 no matter what the input is, as long as you're in this window x is bigger than 2. Let's see, can I squeeze this here? I think I can. We'll do more of a right-hand heavy graph. Up to 4. So 1, 2, 3, 4. Those are my x values. And then my y values, we've got 1s, 3s, 4s, and 5. So we need to go up to 5. 1, 2, 3, 4, 5. Spacing this as evenly as I can without pulling out the ruler and the protractor and all that stuff. All right. So in blue, I'm going to do the top function, the thing that went up to the 2 but not past it. So 0, 3, that is right here, left to right 0, up 3. 1, 4, that's right 1 and up 4. Remember, you've got to have your graphing abilities, just plotting points on, or sorry, up to speed here. And then 2, 5. Now, the 2 was included in that top one, so I will continue to do solid circles. And now we just connect, and normally we connect and extend in both directions. I'm going to say real quick, this is wrong, this is wrong, this is wrong, this is wrong, this is wrong. This is wrong because this section isn't valid because it's only supposed to be for x values less than or equal to 2. So let's get this right. It stops where x equals 2, so this is only going to point down and left. So it stops right there. At x equals 2, there are no x values for 3 or 4 or 5 for that top function because it stops at 2. Why do I know it says it stops at 2? Because that right there says it stops at 2. Pay attention to the details. Use your eyes, use your brain. All right, in red, we'll do the other part of the function. This is all one graph. I'm just showing the colors for the separate functions. So we've got the point 2 comma 1, but that one we said doesn't actually get included. It's the border, but without the or equals, we have to do an open circle. So 2 comma 1 is right here, but I don't fill that circle in. Then 3 comma 1 is here, and 4 comma 1 is here. And then we just connect and extend, but these are only valid for x is bigger than 2, so we're not going to move this thing to the left of 2. We only start at the positive 2 and go right forever, and it's a horizontal line. So the blue and the red combined make this function, and it is a function. It does pass the vertical line test, even where it looks a little wacky, because it only touches here. It does not touch at the bottom one, the red one, because it's an open circle. So yes, that is a function. That is the graph of that piecewise defined function. And again, we have seen things that kind of look like that before. Right here. Here's one that kind of looked like that. Now you might say, well, Mr. Beckner, this one is connected. Even though it changes radically, it's connected. Well, sure, that can happen sometimes. Or sometimes they don't have to be connected. They can have what we call discontinuities. So this is a sudden radical change, not only in terms of growth, but in terms of output. All right, ignore that for one more example. Let's give ourselves some space. Whoa, that was weird. I bet if you count the number of times I say that in a semester, it'll be in the triple digits. I'll give you one more for free. That was weird. Nothing actually weird happened though. All right, B. F of x is equal to curly brackets, so we can tell it's a piecewise defined function. 2x, not plus, that's a minus 3. Minus 3. And that's going to be valid whenever x is negative. And then 2, no, not a 2. X minus 3, just removing the 2. And this is going to be valid when x is 0 or positive. So again, we have a top and a bottom function. I described last time that there can be a middle function. We have piecewise defined functions that have infinitely many functions. We have something known as the Hessian function or the step function, which literally just says the output is 1, then 2, then 3, then 4, then 5 for all decimal values up to the next integer. So if you inputted 2.5, the output would be 2. If you inputted 2.9, the output would be 2. But the second you go to 3, the output's now 3. You input 3.2, the output's 3. When you input 3.9, the output's 3. And it's a cool function because, I mean, it literally looks like a bunch of steps. But that's not what we're doing here. F of x equals 2x minus 3 when x is negative, x minus 3 when x is positive or 0. So for the bottom function, I'm sorry, why am I writing bottom? I'm thinking x is less than 0 for the top function. Let's do a table of values. Now, I can't do 1 or 2 or 3 because this is only valid for negative x's. So let's go from -2, -1, and then 0. But please note 0 is not supposed to go in this technically because it doesn't have the or equals. However, for graphing, it's necessary to plug in so we can see where the border is. All right, so the work, the y, or the f of x, however you want to write that, you can write f of -2 or y equals, nobody cares. That'll be 2 times -2 minus 3. Not going to show all the arithmetic. That's -4 minus 3, which is -7. So go here. We plug in -1. That's 2 times -1 minus 3, which is -2 minus 3, and that's -5. We plug in 0. That's 2 times 0, not just 0. Minus 3, which is 0 minus 3, and that's -3. So there are our 3 points for the bottom function. And by bottom, I just mean top, bottom. I don't necessarily mean one's going to be on top of the other in the picture. That's a completely different meaning, and they wouldn't be functions probably. These are positive x values starting at 0. Now the 0 is included in this one, so I'm not going to put a little asterisk. 0, 1, 2. Technically, you don't need 3 points for either of these because all of the functions I've given you so far have been lines. You only need 2, but they don't have to be lines. They can be a little crazier potentially, but this is what we're sticking with for now. So the function is x minus 3. So we'll get y equals 0 minus 3, which is negative 3. Or y equals 1 minus 3, which is negative 2. Y equals 2 minus 3, which is negative 1. So there's the 6 values we're going to plot this time. Now we got a lot of negative y values, so I want to make this a bottom-heavy graph. But we do have positive and negative x values, so I want to make it pretty symmetric that way. So x, y. Now, I'm only doing this way because I have very limited space. If I had an entire page to graph this, I would make all of them very symmetric plus signs. All right, so x values, we're going to go from from negative 2 to 2. Try and space as evenly as possible. Okay, and then for the y values, we're going down to negative 7. Negative 1, negative 2, negative 3, 5, 6, 7. And I'm only going to label the bottom one just because it's going to get a little crammed in otherwise. All right, so in blue, the quote top function in blue, we're just graphing this stuff. Negative 2 comma negative 7, that's left 2 down 7. Negative 1, negative 5 is left 1 down 5. And then 0 comma negative 3 is right here, and I'm going to make a mistake for a second. This is a mistake, this is a mistake. Why is this a mistake? Because it's only valid when x is less than 0. I just plugged in 0, but it's not valid, so instead of using a closed circle, I was supposed to do an open circle, like this. That shows that it doesn't have the or equal for that particular piece. And then we connect them. So you know at least you're going to connect the 3 dots like this, but you might go, well, do I extend both ways, just one way, and if just one way, which way? Well, this is only valid for negative x values, for when we're going left on the x-axis. So we can only go down and left. If I did this, it would be wrong. Don't do that. This is right. Now for the bottom function, we'll pull off the red. Now here's where things get cool. The 0 comma negative 3 is exactly in the same location as the blue from the top function. So now this is what's cool is this point actually gets shaded in, even though it's not included from the left side, because it's included from the right side and is at the same point. This is no longer a discontinuity type like A was. And then the 1, negative 2 would be right here, and the 2, negative 1 would be right here. So this is just a less steep line, and it's only valid for positive x values, so you don't do this, then it would obviously fail the vertical line test. There we go. So this point right here was super interesting because from the left side, from the top function, we weren't including it, so we had an open circle. But then when we graphed the other half of the function, we ended up including it, which means it is not a discontinuity. It is completely connected. And you would not say it's not a function. It's oops, not highlighter. Well, good enough for now. But this point is only touching once because it had a closed circle and an open circle. The open circles don't count. Open circles are just there to show you a border, a non-included border. So again, piecewise defined functions can be very important for modeling things in the real world. Again, I think I used last time, like trying to model the economic output or something like that. And, you know, disregard the negative x values here, but oh, we're increasing pretty steadily. And then, you know, something pretty significant happens in March and it's slowed down. Now, in fact, our economy, you know, dropped significantly for a while and kind of came back up. But it was almost so sudden that it felt like this, like, oh, we're cruising, and then boom, just flatline. All right. So that is how we evaluate and graph piecewise defined functions. It's not something that we will see a lot of in this course, but it is something that will come back periodically throughout your math courses. All right. Next up. Now, I noticed something about this next topic. There is only one question in your homework for this topic. I do not like that at all. However, I'm not supposed to add extra homework problems because it's departmental. It's just supposed to be the same across the board. I'm going to have some discussions with other teachers as to why there's only one of these problems, because that's nonsense. Y'all should have like 10 of them, in my opinion, but I also think y'all should be doing 2 or 3 times as much homework than you actually are. So no one's going to like my opinion there, but you definitely need more than one of these problems. This is important. When you go to calculus, the first like 3 weeks, 2 weeks, you're going to be spending doing stuff like this. Difference quotients. So this is a formula that when you get to calculus, you will have to memorize, and there'll be something extra attached to this. It's a limit, which we're not going to talk about in this course officially. But this little formula right here, f of x plus h minus f of x all over h, is what we call the difference quotient. The reason we call it a difference quotient is because, well, there's a difference in it, and this long bar that makes it a fraction also makes it called a quotient, because fractions are divisions, divisions are quotients as an answer. So we call this a difference quotient because it's got a subtraction and a division. So the name is kind of, it doesn't really tell you what you're doing, it just says there's a subtraction and there's a division. But this difference quotient opens up the entire world of calculus. This right here is the study of change as you take 2 points, say you're trying to find the slope of a graph, as you take your 2 points and you merge them together. That's what this thing does ultimately. Now, it's not what we're doing here, it's what you're doing in calculus. So you have to be given an f of x in order to do this, or a y equals or whatever, but it's generally written in f of x. So the first thing you do is, you'll do is this. You'll find f of x plus h, which we have shown you how to do back in 2.1 when we did function evaluations. Sometimes it's simple, sometimes it's ugly. Then what you'll do is you'll plug this f of x plus h, whatever you get, into this thing. Then you'll go minus, and then f of x, this thing was already given to you. That bit was given to you, and then you just write all over h. And then from there, it's just simplify as much as possible. Simplify, 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 and then simplify some more. Until you get this thing to be as simple as humanly possible. Now, how do you find f of x plus h? What in the world do we do? They didn't give us f of 3 or f of 5. They didn't tell us what to plug in. Yes, they did. They just didn't tell you to plug in a number. They told you to plug in some weird other thing that I already alluded to. You plug in x plus h. So all the x's in your function would turn into x plus h. That's it. So I'm not going to make you memorize the formula in this class. This formula will be given to you in a test problem, and I will absolutely give you a test problem with this. But again, in calculus, you'll see it again, and you won't be given that formula. So how exactly do we apply this? What's my first example? Example 4. Silly me. Evaluate the difference quotient given function. We're going to have a simple one. F of x is equal to 2x plus 3. So that's our function, 2x plus 3. Y equals 2x plus 3, or f of x equals 2x plus 3. Remember that f of x and y are interchangeable. They really mean the same thing. It's just writing it as f of x. Guarantees that there's no vertical segments that overlap. And also we can plug anything into it instead of just numbers, which is what we're going to have to do here. So the first thing we have to do is find f of x plus h. What I'm going to do is I'm going to go to this function, and wherever you have an x, which is right here, this x is going to turn into x plus h. So I'm going to keep the stuff I'm not changing in black. and the stuff that I do change in blue. So that'll be 2, then the x, and then the plus 3. So there's some stuff here I haven't written yet. The 2, then the x plus 3. But where there was an x before, I'm now writing x plus h. I can't just do it like this, though, because that looks like it's just a 2x, and then I wrote a plus 3 because that's what I'm staring at, but it was supposed to be an h. So that was right. That was wrong for 2 reasons. This is wrong because the 2 is not being multiplied to the x and the h. You got to wrap it in a parentheses, just like anytime you plug in a sum or difference or negative. When you distribute the 2, you'll get 2x plus 2h plus 3. That's all you can do for the f of x plus h. You can't combine any like terms. There's no distributions, there's no foiling, there's no factoring, that's it. So this is what your f of x plus h is. So in this formula, again, we're going to plug everything into this formula. There's only 2 things we actually plug in, and that's the 2 things into the top. The h is just an h. So this f of x plus h is going to be this right here, and then the f of x is going to be this right here. You're just plugging the circle into the circle, the triangle into the triangle, the pentagon into the pentagon. That's all we're doing. So f of x plus h minus f of x all over h. I am rewriting the formula here, which I could have also just written dq, not Dairy Queen, difference quotient. That formula is equal to, all right, the f of x plus h. Again, the first thing we write is this blue ink over here. That is the f of x plus h. How do I know that? Because it's f of x plus h. So 2x plus 2h plus 3. Once again, this right here is this right here, which was that. Then we have a minus in the formula. Minus. Then what we subtract off is the f of x. I'm about to write something incorrectly, though. So this is the thing we're subtracting. But remember, we're supposed to subtract all of it. If I just do this, this is the #1 common mistake on these simple ones. This is wrong. Why is it wrong? Because the minus is only being applied to the 2x. Got to wrap it in parentheses. And then we have this whole thing over h. Hopefully this one doesn't look too scary, because it's only going to get worse. It's about the easiest example we can do. All right, so let's distribute the negative. That'll give us, hopefully I have enough room, 2x plus 2h plus 3, then minus 2x minus 3 all over h. So our difference quotient. Check this out. Now we're just supposed to simplify. The 2x minus 2x, these will cancel. I'm going to erase my canceling in a second. And then the 3 minus the 3, those are going to cancel. So that whole top is just 2h. Again, the 2x and the minus 2x gone. The 3 and the negative 3 gone. 2h is the only thing left over. So the top is 2h. The bottom, well, that's h. There's nothing we can simplify. There's no pluses, there's no minuses, which means in order to reduce, we don't have to factor. We can just cancel a common pair of h's, top and bottom. So the answer is 2. That's it. And most people go, wow, this problem looked really ugly for a bit, but then the answer ended up being quite simple. It's pretty common for things to go that way. B. Yeah, we'll start it here. Probably end up needing the other page, but that's okay. F of x is equal to x squared plus 3x minus 5. This right here is more like a problem I'd give you on the test. That first one, in my opinion, is too easy. I know you probably disagree with me after only doing one of them, but hopefully we'll get used to it. I would suggest practicing that one and only one homework problem over and over and over and over and over. I would also suggest maybe going to the textbook and finding some in the homework of 2.2 and trying them on your own. You won't have the step-by-step guides to them, but at least you'll have the answers in the back of the book. And that is something that is critical. Again, I personally believe that y'all's homework assignments are entirely too short. I remember we used to give 50 homework problems a section. Don't know what happened to those days. I miss them. I know you don't, but I think it made better students. So this is the function. The first thing we have to do, find out what is f of x plus h, because that's part of the formula. Again, because the difference quotient, this thing right here, to actually progress, we need this. The h is fine, the f of x is fine, h is h, the f of x is given to us, but we have to find that thing I just highlighted. All right, so we're turning the x's in this into x plus h's. So again, I'm just going to leave some little squiggle room for where I'll be substituting it. This was the x and then squared, and then plus the 3, and then that'll be our x, and then the minus 5. But where I have squiggles, that's the substitutions. We don't write x anymore, we write x plus h. This would be wrong because that looks like it's only squaring the h. Parentheses important. To show the x times the 3 or the x plus h times the 3, once again, you need parentheses. Notice I don't put it here. I don't put the x plus h there because there was no x with the minus 5. So again, the blue ink was x squared plus 3x minus 5, but we changed the x to x plus h. Now, I'm going to need more space. This issue has been seen before. We did this exactly earlier in 2.1. I think it was 2.1, where we had like an x squared and we plugged in x plus h to it. You can't just square the x and the h. If you do this, this is another super common mistake, x squared plus h squared. That's wrong. You're missing half the work for that little segment. You're supposed to say, oh, well, that's the parentheses times itself. So that's x plus h times x plus h. Let me go ahead and distribute the 3, so that's plus 3x plus 3h minus 5. And then we need to FOIL that left bit over there. The first will be x squared, x times x is x squared. The outer and the inner will be identical. I'm going to go a little quicker this time since we've done exactly this scenario before. The x times the h is a plus xh. That's the outer. The inner is the h times the x, but you don't want to write it this way because then these two things look different even though they're not. So just be consistent in the order you're writing your variables. If you wrote x, then h, do it again. So the outer and the inner match. The last is h times h, which is a plus h squared. Bring the 3x, bring the 3h, bring the minus 5 down. So that f of x plus h's combine like terms. X squared does not have a like term. Xh plus xh, that's like having apple plus apple is 2 apples. So it's plus 2 xh. Plus h squared, no like term, plus 3x, plus 3h minus 5. So this is the f of x plus h that is going to go in the formula right there. The minus f of x, the f of x is, well, what they gave you. The h is literally just h. You just write the whole thing over h. It's another simple thing to forget is to just write the top, because that's the complicated bit, and forget the over h. But if you forget the over h, you forgot the quotient part of the whole formula. All right, so our difference quotient, which I will write the formula one more time, even though you don't have to memorize it here. The f of x plus h is this blue stuff we just found. So it'll be, and in fact, I'll write it in blue this time because it's a little messier. X squared plus 2xh plus h squared plus 3x plus 3h minus 5. I'll write it in blue here for consistency. There we go. Then we go minus f of x. So minus And then because this f of x had several terms, you can't just do this, you can't just do this, you can't just do this. You need parentheses. Now it's correct. See, this is wrong without the parentheses because it's only subtracting the x squared. Now we're subtracting the entire function. And then we do this whole jazz over h. Now this looks terrible, I know. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9 terms in the top. Holy moly. This has got to be the worst problem you'll ever see in your life, right? He says sarcastically. Well, no. Just simplify. So distribute the negative. Give that negative to those three things at the back. So the first up to the -5, everything up to this point isn't going to change. All the blue ink won't change except I'm making it black now. X squared plus 2xh plus h squared plus 3x plus 3h minus 5. Distribute the negative, so minus x squared minus 3x plus 5 all over h. So our difference quotient. Now this is where the magic happens. X squared, negative x squared, gone. Positive 3x, negative 3x, gone. Negative 5, positive 5, gone. The only terms you're left with in the top are the 2xh, the h squared, and the 3h. It's just those three terms that you're left with. Again, I don't want to leave the canceling shown. The x squared canceled. The 2xh is still there though, so 2xh. Let me just write dq a little lower. The plus h squared is still there. The 3x canceled the negative 3x. The plus 3h is still there. It's interesting that the terms in the top that had h's are what are left. That's pretty common, in fact. The -5 and the +5 are gone. So now we only have three terms. Don't forget the over h, though. Now the top, there are no like terms to combine. So some people will stop here, but that's not good enough. What you can do is notice h, 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 h. There's an h in every single term. So there is a GCF of h in the top. So we can factor that out. So we get h parentheses. Now when we pop a GCF out, that means we're dividing. So we just get rid of the h from each term. So 2xh, get rid of the h, leaves you with 2x, plus h squared, we're getting rid of one of the h's, so we're still left with a single one. Then plus, we'll just be left with the 3 from the 3h. If you don't trust this, distribute the h back, you'll get the same thing. And then all over h. And then, because this is now in a factored form, there's an h in the top that's factored with an h in the bottom that's sole by itself. They cancel. So this whole thing is equal to 2x plus h plus 3. And that's the answer. Pick a different color. If you don't like factoring a GCF out of the top, so when we were to this point, 2xh plus h squared plus 3h all over h, if you recognize, hey, there's an h everywhere, which some people do is they'll just cancel it out. They'll say there's an h, then this h squared becomes an h to the first, this h is gone, and this h is gone, which makes the whole thing just equal to, there's a 1 in the bottom, so you don't need to write it, 2x plus h plus 3. The same answer. I don't care if you're factoring a GCF and then canceling, or if you're just canceling on the spot. But remember, to cancel, it has to be everywhere if you're using this orange method. So if there was no, if this h wasn't here, if this was just 2xh plus h squared plus 3, I couldn't have done that because the h would not have been everywhere. You have to be very careful if you're going to use that last method. Very, very careful. But again, I don't care which way you do it. So here's what I love about this problem right here. And the last one. You just did calculus, except for one very, very simple, ridiculously simple final step. In calculus, I give this exact problem to calculus students. The only thing they do at the very last second after they get this, instead of boxing it up, they make the h 0, and then this is their answer. That's the only difference between what we just did and a calculus student. They make the h go away. You might say, well, what's the whole point of that? Then just don't do any of this h stuff, right? Well, no, there is a drastic point that we won't get into, but that is what this whole thing is about. Something even more fun is I teach calculus students how to do this whole problem in about 2 seconds. And it's not just me teaching them, all calc teachers teach them. So looking at this right here, I could tell you the answer was going to be 2x plus 3 in the calculus course. Now that h, there could be a number with the h somewhere. I can't tell you that part in 2 seconds. But in calculus, I can tell you that answer would have been 2x plus 3. In calculus, I could have told you the answer to this one is 2. And again, 1 or 2 seconds. I mean, that one would take a quarter of a second, honestly. All right, so difference quotients. You don't have to memorize the formula. It will be on the test problem, but you will see it. You will see it again, assuming you're going to calculus. It's a good topic, one of my favorites, because it's a gateway problem. All right. Let's talk about symmetry. So we got 2 main topics, both relating to each other before we close out 2.2. And they are symmetry and the concept of being an even or an odd function, or neither. But let's save that last one for a little later. Symmetry. Symmetry is all about mirrors. Symmetry is helpful because if you draw, say, the right half of a graph and you know it's symmetric with the y-axis, you can draw the left half by just mirroring it. Or if you have an equation where you've drawn the top right half and it's symmetric about the x-axis, then you just mirror it down. If you have something that's symmetric about the origin, then you use both mirrors. You mirror it left and then you mirror it down. And when I say left, I could say right instead, or when I say down, I could say up instead. It just depends on where the function was originally. So again, the idea here is a graph is symmetric about the y-axis if the left side is a mirror image of the right side. Let me get a little more space here. There we go. So let's show what I mean there. And what I like to do when I'm in person is I say, all right, imagine that you just drew let's do a little better than that. Let's say you just drew the right side of a graph. You figured out x equals 0, 1, 2, 3, 4, and 5, and then this is what it ends up looking like. And you determined that that function is symmetric about the y-axis by some method, which we'll get into soon. So what I say is, imagine that your y-axis, you're going to fold your piece of paper there. So this is our mirror for the symmetry about the y-axis. So when you fold your piece of paper along that mirror, if your ink is wet, it would then transpose the graph over here. So the black ink is me drawing the right side. I know it's got this symmetry because of a test that I can do. And then boom, you get the other side of the graph without having to do -1, -2, -3, -4, -5. It's a time-saving element. So this was the y-axis symmetry. If you have x-axis symmetry, which is the second one up there, that just means that the x-axis is your mirror. So that's your mirror this time. So if I were to draw, say, this part of a graph, I'm not calling it a function, I'm calling it a graph or an equation. And then I said, okay, I have determined that this graph is symmetric about the x-axis, so it just mirrors up and down. So then I know that the bottom half would look like this. I could make that happen automatically with wet ink, piece of paper, and fold where the mirror is, and then it would just transpose there. But without folding and everything, you just have to, gauge it visually. Now, the middle one is the least interesting to us. You know why the middle one is the least interesting to us? It's not a function. You can make that little memo somewhere if you like. I'm about to erase it. But the middle one is not that interesting to us overall because we primarily deal with functions in this course, primarily. And things that are symmetric about the x-axis are not functions. I mean, literally by definition, if you mirror the top to the bottom, you're going to create something that's not a function. It's an equation. Sure. And that's a wonderful equation. It's the equation x equals y squared, but it's not a function. Okay. What about this bottom one? A graph is symmetric about the origin if the x and y axis are both mirrors. So you draw the original bit, maybe it looks like this. We'll go back to that quadratic looking one. So that means that you have a mirror on the y-axis and you have a mirror on the x-axis. So in orange, I'm going to do a middleman. So you have to reflect it both ways. So I'm going to reflect it left first, then down. The order you reflect it doesn't matter. So I'm going to do it dotted. So this is me with the first reflection. So there's the y-axis symmetry, but this isn't actually the graph because if we say if it's symmetric about the origin, you do this, then the other, and then you end up down here when you do the second reflection. And you can see, I think, pretty clearly, let's just call this the middleman. If I had done it down and then the other way, here's your middleman, which I'll erase, and then you'd end up reflecting it across the other and getting the same image. So the solid orange part along with the black part is the actual curve. So again, the actual curve, the actual function is this. Please ignore my terrible drawing that time. That's the function. And it is a function because it would pass the vertical line test. So symmetric about the y-axis, they're functions. Symmetric about the x-axis, they're functions, generally speaking. Symmetric about the x-axis, never, ever, 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 ever functions. So I'm not going to really discuss the middle case too much because it doesn't really pertain to anything moving forward. But we will discuss the first and third cases because those are what describe even and odd functions. So I'm going to go ahead and give you a little memo here that this first one, let's go back to blue here. We'll explain why in a second. This first one is an even function. This third one is an odd function. That's how even and odd functions look like. Even functions are symmetric about the y-axis. Odd functions are symmetric about the origin, which means you have that double reflection. Even functions, you can reflect left and right. Odd functions, you have to reflect left and down, or right and up, or right and down, or left and up, whatever the combination is. Why do we call them even and odd functions? It has something to do with the exponents if they're in polynomial forms, but that's not a big enough, or is that too? That's a generalization that doesn't always work. Let me say it that way. The basic idea of why we call them even and odd functions is because a function that only has even exponents typically ends up being an even function, and a function that only has odd exponents typically ends up being an odd function. Notice I use the words typically. There are even and odd functions that don't even have any exponents or polynomial terms. You can have the absolute value function, that's even, but there's no exponent, and other cases as well. Because an absolute value function looks like this. This is our absolute value function, as we'll learn soon enough. It looks like a V, so there would be a mirror right here. You don't have to draw the right side and make the left. You can draw the left and get the right. But again, it's just the idea of time saving. All right, so what exactly is the pure definition of being an even or odd function? Too far? Yes, too far. I'm going to pull back in a minute or two once we see those and get them written down and everything. Even functions are such that it just means something is an even function if this happens. F of negative x is equal to f of x. So in other words, I give you an f of x, and if it's even, this is the thing you have to do, and then you try and find out if they're the same. So you're given this, and you have to find this. Well, how do you find f of negative x? We've literally done that as an example 1 or 2 classes ago. You just take the x and you change it to a negative x, kind of like earlier where we were taking an x and turning it into x plus h for a difference quotient. So that was why I had an example of doing an f of negative x earlier, because it's related to even and odd functions. So if f of x is the same thing as f of negative x, in other words, if the sign of x doesn't affect the output of the variable, if the sign of x doesn't affect the output, you end up having a graph that looks like this. The same thing for absolute values. Plugging in 3 gives you the same thing as plugging in negative 3. Or for x squared, plugging in 5 gives you the same thing as plugging in negative 5. This says that the sign of x is irrelevant. You get the same output either way. But the test for it is to compare the original function to taking the x and making it negative x and seeing if everything is the same. Now, sure, you can graph the functions, and if you see that symmetry, then it's even, but that would be a much longer process. So a function is odd if, again, this just means if, f of negative x is the same thing as negative f of x. So even functions, it's positive f of x is f of negative x. Odd functions, it means if you have a negative outside the function, it's the same as if you plugged in a negative to the function. So this is not comparing f of negative x to the original function, it's comparing it to the opposite of the original function. How do you find the opposite of an original function? You just slap a negative in front of the whole thing. Negative, parentheses, boom, there's your opposite. Distribute it and you're done. It's easy. So if the opposite of a function is the same as plugging in the negative, that means they're odd. And the core idea there is that you're replacing the x with a negative x and the y with a negative y. That's what it means to be odd. The third line is just the process. So the first thing you should do is find f of negative x and then see if they're even, because seeing if they're even only requires one processing. If it's not even, then you want to go, well, if it's not even, maybe it's odd, because a function can't be even and odd, just like a number can't be even and odd. So if the easier case doesn't happen, if it's not even, then you go, well, maybe it's odd. So then you'll find negative f of x, which again just means take the original function, slap a negative in front of the whole thing, and distribute it. So if these two highlighted things are the same, then it's odd. Well, what if neither of those scenarios happen? Well, then the answer is neither. Just like 3.5 is neither even nor odd, and 2.2 is neither even nor odd, there's actually more non-even and odd numbers than there are evens and odds. And in the same respect with functions, there's more non-even odd functions than there are even functions and odd functions. Oops, too far. The last two lines are just the things that we described earlier, that even functions are symmetric with the y-axis. So that top highlighted one is here. This is symmetric about the y-axis. It's even. And then odd functions are symmetric with the origin, which means you flip across both. Again, the order you flip doesn't matter. You can flip down and left and down, or if you're going right and up, if that would be more relevant, either way. It's very easy to look at a picture and tell it's even. It can be a little more difficult to look at a picture and tell it's odd. But again, if I gave you the graph, you cut off one of the sides, flip the other side until it matches or doesn't match, and that tells you whether it's odd. But again, this case right here, we're not really interested in that much because it's not a function. So a lot of people think that that middle one would be odd. If this is even, this has got to be odd. But if it's an even function, this can't be an odd function because it's not a function. So that's kind of the primary reason as to why this is an odd function, not the middle case. How are we on time? About 20 minutes. Examples. What number are we up to? Example 6, example 5. Sorry for the scrolling. Example 5, even, odd, or neither? Question mark. a, and have f of x is equal to x to the fourth plus 5x squared. Now, I said something earlier that I don't even like saying, because a lot of students will just look at this and they'll go, oh, well, it's even for this reason, or oh, it's odd for this reason. You've got to show the work. Because the problem with this is, in homework and test, is there's no partial credit for it. You'll just answer even, odd, or neither. So if you think you deserve partial credit on that and you emailed me, if I don't see the work, you're not going to get partial credit. Because there are ways that you can look at these exponents and you'll think you have the right answer, but I can do a little trick and make it wrong. Okay, so that's why we're going to do all this process. So try and see if it's even first because it's less work. So the first thing we need to do is find f of negative x. So that means the x's here and here will turn into negative x's. Now, because I'm plugging in a negative, you guessed it, we need to wrap those negative x's in parentheses. So this is the negative x, but then it's the fourth power plus 5, and then the negative x being squared. Now, we've seen this type of problem at least once before. A negative to an even power is a positive. So the negative x to the fourth is actually still just a positive x to the fourth. Negative squared is positive, so that's still a plus 5x squared. So then what we're asking is, if it's even, this is what should happen. The thing that we just got would be the same as the original function. That's what that thing I just circled says. The thing that we just got, the f of negative x, has to be the same as the original function. Well, look at this. The original function and that are exactly the same. So it's even. Oh, take off the highlighter, silly. F of negative x is equal to f of x. So it's even. I'm not even going to do this. I'm not going to do negative f of x, because if it's even, we know it's not odd. We know it's not neither. It's even. That is really nice when a function is even because it's a little less work. What if we had f of x is equal to, how about 3x to the fifth plus 2. So again, some people will say, oh, well, Mr. Beckner said even exponents means the function's even. Oh, even exponent, so it's even. And yeah, that happened to be true there. So all I see is an odd exponent here, so this must be an odd function, right? 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 Lots of inflection. Let's show our work and find out if that's the case. So first thing, let's pretend you didn't even hear all that stuff. It still could be even. And even if it isn't, you still got to do the f of negative x anyways, just to check if it's odd. So turn the x's into negative x's. So we get 3 times negative x raised to the fifth power plus a 2. There's no x here to plug into, which is why the 2 doesn't get one. Well, a negative an odd number of times is still a negative, so this is negative 3x to the fifth plus 2. Now the 2's are the same. Those are the same, positive 2, but this was a positive 3x, and this was a negative 3x to the fifth, so they're not the same. Not even. So this is where we go to the second step. This is where we try and find negative f of x. I'm not plugging negative into the x anymore. That's not what I'm doing. I'm not plugging a negative there anymore. This is a negative in front of the whole function. So we just write a negative, and then we write the whole function, but because of the negative, we'll need to surround it in parentheses. Again, take the whole function, but put a negative in front of it. That's negative f of x. This is essentially just changing the y to a negative. That's what we're doing here, whether you see it or not. Distribute the negative, and we get negative 3x to the fifth minus 2. Be careful with your signs. Now, if this was odd, then the thing that we just got would be equal to the thing we got from the end of the first step. Again, if this function was odd, then this, what we got from the end of the first step, the f of negative x, would be the same as the negative f of x, which we just got as this. And they're close. The first term is the same, but the second term is not the same. So even though it's half right, that's not good enough. It's not odd. Which means the answer is neither. This is kind of like a decimal value, 2.8, 3.4, pi. There are even and odd functions. There are a very small amount of functions that are actually even and odd. However, the basic functions without lots of extra terms tend to be one or the other. But we're going to study the basic functions and then build and build and build, of course. So I did not give you an example of one that turned out to be odd, but I will at least show you an example of one that would be, and I'll ask you just kind of show it on your own. So C asterisk, I'm not going to complete this, but show f of x equals 2x to the, I don't know, 9th minus 5x to the 7th plus 3x is odd. That function will end up being odd. So you'll have to go through the first and second step, and then those two things would end up being equal to each other. But still, you know, ask yourself, is it even? Do the first step. Notice that it won't be the same, so you can say it's not even. Do the second step, and it should be the same as the end of the first step, which means it will be odd. All right. Got about 10 minutes left. Let's not waste our time. Let's dive into 2.3. So please understand that 2.2 slope. Again, there's a lot of material in pre-calc where we are just kind of reiterating things from before. And it's interesting how we'll do topic A in here, but not topic B again. Like we aren't really supposed to reteach factoring, even though I did spend like 30 minutes kind of setting it up. But graphing lines, which I honestly think is very simple, I guess it's just students don't think it's simple, so they forget it and we have to reteach it. Don't you dare ever forget how to graph a line again. I get students come to calculus and they can't graph lines. That terrifies me. They can graph crazy curves, but then they forget how to graph a line, the simplest thing. Got to know your basics. You can't do a million plus a million without doing 1 plus 1. So lines are lines. They're straight. Straight line is a redundant statement. All lines are straight, but in the media, that's poorly stated constantly, and they'll draw a curve and call it a line. Or you might see in statistics, they have this thing known as a line of best fit, which they don't always end up being lines. So it's kind of a poor name, but you know, statistics is statistics. Any line can be formed by just 2 points. This is a point, sorry for the pun, that I made earlier when we were graphing those piecewise defined functions, that while I did 3 points, we technically only needed 2 as long as we knew there were lines. Every line has a constant slope, which means the steepness does not change, that can be calculated, that can be found by calculating the rise over the run. So slope, by definition, per run. Right, so I gotta add it up here. So a line going through 2 points. Write this way just to be quicker. X1 comma Y1 and X2 comma Y2. That's slope. And we use the letter M to denote slope. m equals y2 minus y1 x2 minus x1. This is a formula that you must memorize. You do not ever get to forget this. If you're going to pre-calc 2, you don't get to forget it. If you're going to calculus after this, whether it's regular or business, you don't get to forget it. It's such a simple formula too. The idea, again, is that it's the rise over the run. This is also the change in height over the change in the horizontal position. Change is a difference. The change in height divided by the change in horizontal position. Change is subtraction. So it's a ratio of changes. Also known as a difference quotient, but it's a slightly different formula. This m right here, this formula, has everything to do with that difference quotient we did earlier, but the difference quotient's a little fancier. So it sticks its pinky out when it's drinking tea. Memorize it, don't ever forget it. So graphically speaking, let me give myself just a little space. And I'm only going to draw the top right quadrant, just again in terms of space. Let's say we had this point right here, and then this point right here. So this point would be x1 comma y1, and then this point would be x2, that looks like a y, comma y2. So this x value has to be x1, this x value has to be x2, this y value has to be y1, just tracing over to the axes, this y value has to be y2. And then here's the line that connects them. The rise is the vertical distance between points. That's the rise. The run is the horizontal distance between the 2 points. So slope is just the ratio of these two distances. When you form a little right triangle out of the line, in a horizontal and vertical manner, so that's a 90-degree angle right there, your slope is just the ratio of those two things, which when you go to trigonometry, you're going to study right triangles a whole boatload. Heavily relates to the tangent function, but we're not going to talk about that today. So slope is a measure of how steep a line is. The steeper the line, the larger the slope. Lines can have positive slope, they can have negative slope, they can have zero slope, or they can be undefined. So maybe you have this line, and this slope is, I don't know, 2. Then you have this line, and this slope might be 4. The steeper the line, the larger the slope. That's what I'm trying to say with the top line. Slope is a measure of how steep it is. Lines that have a positive slope go up and right, they're increasing. Lines that have a negative slope go down and right, they're decreasing. So a line that looks like this, they don't have to go through the origin. This would be a positive slope. A line that looks like this would be a negative slope. A line that looks like this, horizontal line, would be a 0 slope. And a line that looks like this, vertical, would be an undefined slope. Now, the last two cases, you can actually see algebraically. If you plugged in 2 points, let's say you found out what this coordinate and this coordinate were, if you plug them into the y2 minus y1 over x2 minus x1, you would end up with 0 because the top would be 0 because they have the same heights. That height's, say 5, this height's 5, 5 minus 5 is 0. So the top's 0, which means it's 0. If you did this one though, they have the same horizontal position, maybe x equals 5. So in the bottom, you'd be doing 5 minus 5, which is 0, but dividing by 0 is undefined. For the love of math, don't you dare ever get that wrong again, that 0 in the top has to be 0. 0 in the bottom has to be undefined. All right. Again, like we said, kind of going slightly quick through this because this is retreading old material. So for example, 1, and there will be a B and a C, you just don't see it yet. Calculate the slope of the line going through. That'll be A. For B, we're going to do 6, 1, and 6, -8. For C, we're going to do 1, 5, and 3, 9. Only got a couple minutes left, so we might not finish all these, but we'll do our best. All right. What I suggest, especially at first, is that you label these as x1 and y1. It doesn't matter which one you call the first point. If you choose to call this the first point, then this is x1 and this is y1. I know it looks like an x. There we go. Now I'd make this x2 and y2. However, I never do things that way personally. I go in order. But like I said, it's up to you. So this is x1, this is y1 for me, then this is x2 and y2. They have to be paired correctly, and it's always x, y. It's not x1, x2, y1, y2. That's wrong. So our formula for slope is y2 minus y1 over x2 minus x1 that you're supposed to have memorized yesterday. So y2 minus y1, that's 7 minus -5. Notice how I'm careful with my negatives. Over x2 minus x1, that's -2 minus 3, which is 7 plus 5 in the top over -2 minus 3. So the slope, 7 plus 5 is 12. -2 minus 3 is -5. I've said before, I don't like negatives being left in the bottom, so let's write it in the front or in the top. Slope is -12/5. Can't reduce that fraction. We had enough time to do these. For B, the slope is y2 minus y1. If you need to label them, x1, x1, y1, x2, y2. So your slope is y2 minus y1, that's -8 minus 1, over x2 minus x1, which is 6 minus 6. -8 minus 1 is -9. 6 minus 6 is 0. You cannot divide by 0. It's undefined, which says that would be a vertical line. If you plotted those 2 points, you would see a vertical line when you connect them. And then for C, M equals x1, y1, x2, y2. If you don't have to label them and you can get it right, then don't label them. y2 minus y1, 9 minus 5, has to be the y's on top. You can do 5 minus 9, but then in the bottom, while I'm going to write 3 minus 1, you would write 1 minus 3. 9 minus 5 is 4, 3 minus 1 is 2, and this reduces to 2. Sometimes your slopes are written as fractions still, sometimes whole numbers, sometimes 0, sometimes undefined. Depends on the problem. So we're going to call it a day there. We're about...
All right, sorry for taking a couple extra minutes of your time. So I'm just cutting that little talk short. Just for the last 20 seconds of class, your due dates, test details, all that stuff. So we'll be back on Tuesday. Remember, those tests are automatically graded, so you'll get input immediately. And like I said, if you think you have good work that would get you partial credit, you can email me. Make sure you say Math 161 Test 1, something like that in the email title. And hey, Mr. Beckner, I think I have good work for question 2, 15, and 19. Can you see if I have any partial credit? And then I can scan. All right, so again, email me with any questions. Work hard, do well on this test, and we'll see you on Tuesday.